All right, guys, so we are continuing 9.2, okay, and we are starting out with test polar equations for symmetry. So in the box it reads, symmetry with respect to the polar axis, aka the x-axis. In polar equation, replace a blank, okay, so the first blank we are going to do is, let's talk about this point that we have here. I'm going to try to stretch it out. So let's just say that I give you a point in quad 1. Okay, here's a point in quad 1. And if we are doing a reflection over the polar axis, aka the x-axis, whatever's in quad 1, it is now in quad number 4. Whatever's in quad 2, it is now in quad number 3. So the easiest way is to change the angle, right? If we are going counterclockwise, and keeping the radius positive, to reflect it, all we have to do is now going clockwise and still keeping the radius positive. So for this theorem, we go, okay, well, just take out your original theta and replace it with a negative theta. If an equivalence equation results, the graph is symmetric with respect to the polar axis. Okay, now just like in math, as you know, there's always, right? We always have multiple ways of doing things. So what if we don't want to do replacing theta with its negative theta? Well, another way of doing that is, okay, well, let's just say I have it in quad 1 and I want to reflect it and put in quad number 4. So another way to go about that is I can go all the way here, okay? I can go all the way there and then do a negative radius. Would you agree? So if I go all the way there, I'm trying to see if I would be having this right here as my ray. And because it's you know what, let me just continue this out just to make this easier to see. Okay. So if I go all the way to quad 2, okay, the reference angle's got to be the same, so I'm going to get a different color here. Bam, bam, bam. Those reference angles are exactly the same. So whatever reference angle we have, I'm going to take pi, that whole thing is pi, and minus my reference angle. So that's this angle right here. So this right here is pi minus theta. But that's quad 2. So to get quad 4, I have to use negative radius, okay? So a second formula, or another formula would be, negative radius and then pi minus theta. So that's another way to test for symmetry with respect to the polar axis. Now, let's go to the next one. Symmetry with respect to the line, theta equals pi over 2, aka y-axis. So if we have something in quad 1 and we want to reflect it over the y-axis, now it's in quad number 2. If we have something in quad 4, it would be in quad 3. So again, all we have to do is end in quad 2, and these right here, those are the reference angle. They have to be exactly the same. So we're going to take pi minus the reference angle, and we do want to be in quad 2, so the radius maintains a positive measurement. So what we want to say is take out the theta and replace with pi minus theta. If an equivalent equation results, the graph is symmetric with respect to the line. Theta equals pi over 2. And just like earlier, we do have another formula as well. Okay, so mind you, I want to be in quad number 2. Okay, but to be in quad 2, would you agree that let me just make all of these extra so that's easier to see and get a different pen here. To get to quad 2, I can go this way, which is a negative angle, which is a negative theta, but I want to be in quad 2, so I don't draw my radius here. I go the other way to draw my radius. So that's why it's a negative radius. So another formula is that you can change radius and you can change negative angle as well. So you can do both. All right, let's go to the next box. Symmetry with respect to the pole, aka the origin. So this is, back in the days, we call it an odd function, right? So let's say again, we have an original dot in quad number 1, and I want to be in quad 3. The simplest way to go about that is to replace by negative radius, because then that will make you go the opposite direction. So if the exact equation appears, then you have a symmetry with respect to the pole. Well, same thing. We should always have another formula. Would you agree? So I want to be in quad number 3. Let me extend this out. There you go. Okay, that's where the symmetry is. What if I don't want to replace radius? Okay, then that's okay. You can also go all the way to here, just like that. This is the reference angle. This is the same reference angle. So that ginormous angle is really theta plus, oh, how about this? I'll write pi plus theta, because theta is like your reference angle. So we can do pi plus theta, and then we can keep radius exactly the same. So another formula would be, keeping radius exactly the same, and then just take your pi and add your reference angle. All right. Okay, so now I'm going to need to find my decimals, because it says explore. But you know what, before we go to the exploration, I do want to make a point with this one. I want to highlight this right here in this formula. So guys, this formula right here will work about 90% of the time. Okay, again, this will work about 90% of the time. What if you're doing a symmetry and none of these three, okay, it's symmetric, but you know that it has to be based on your graph on the calculator or based on your graph on decimals? Then what you must do is 10% is really this formula right here. So again, percent is this third equation will work 90%. Okay, and the easiest one is always just replacing radius with a negative radius. But there's that 10% that you know in your gut that there is a symmetry, but somehow it's coming out to be none, then you have to use this last one. Okay, unlike the first two, guys, the original formulas here will always work, so you don't have to worry about this another format. But the last one is the one that if nothing works, then I need you to try this last one in green with the star. Okay, let's bust out our decimals. It says using a square screen, graph r equals 3 minus sine of theta, which I will now find my decimals. I'm going to type in, make sure we are in polar on decimals. So I'm going to change my grid to this grid. I want a square, so let's go -10 to +10 on the x and y both. And let's type it in, r equals 3 minus 3 sine of theta. Okay, I'm working this first one out with you, and I want the next one as well. What easiest for me is just copy and paste and change my addition sign. There you go. So it says, so the red one is, oh, that's pretty, right? And the blue one, oh, that's cool. So let's go back and see what it wants us to do. Using a square screen, graph r equals 3 minus sine of theta. What pattern shape do you see? You can fill in that part on your own. To me, it looks like, okay, a peach, a nectarine, something like that. You can write whatever you want on there. So this is really what you see. Then number 2, I happen to also type that in for you. Also fill that out. That's something that you can do on your own as well. How are the above 2 questions different or similar to each other? You can also fill that out, right? So all of that is really your observation of the 2 equations. Then, oh, I got 2 number 2s. So let's change that to number 3. Number 3, using a square screen, do both of that again and answer the blank spaces. So go ahead and do all of that on your own. And then once you're done with that, you can hit unpause to fill in the next part here. Cardioids. I know I said earlier it looks like a peach or a nectarine. It is called a cardioid. Cardioid is a heart. Okay, so cardioids, the equations are equations. You have r equals an a value in the front. We can do 1 plus cosine of theta, or 1 minus cosine of theta. Or we can also have r equals an a in the front. We can do 1 plus sine of theta, or 1 minus sine of theta. So those are the equations for cardioids. Where a must always be bigger than 0, so a has to be positive. And the graphs of a cardioid passes through the pole. So what does that mean? That means it goes through the center. Okay, so once you got that down, we are going to go all the way to 1e and complete 1e. A, B, C, D, we did that already, okay? Now it says here, on a normal year, we would graph all of these by hand, but this year we will use a graphing device for graphing. But you still have to complete the test for symmetry by hand. So, symmetry test by hand, it says. Okay, let's rock and roll. We have 3 symmetry tests. The first one is the symmetry with respect to polar axis. So, polar axis. Now, whatever you do in your homework, the best way for you guys to work this out is to write down the formula. Okay, so replace theta with negative theta. Okay, r equals 1 plus cosine, take out the original theta, replace with negative theta, and this will give us 1. Remember, cosine is an even function, so what does that mean with an even function? Even function. Okay, we talked about this from the review unit. F of negative x equals to f of x. So you have a negative angle, it is exactly the same as having a positive angle. So this is immediately symmetric with polar axis. Yes, do both of them, or do all 3 of them, because sometimes they will be all 3. So next we want to do symmetric with respect to the line. Theta equals pi over 2, and yes, sometimes it will be all 3. And the formula says replace theta with pi minus theta. So r equals 1 plus cosine, take out theta, chuck in pi minus theta, and from here you do have to use the sum and difference of cosine. So 1 plus cosine of alpha, cosine of beta, okay? And why don't you fill up the rest, and then that way you can come back and check with me to see what happens. Okay, so hopefully you got to here and you wrote plus sine of pi and sine of theta. Okay. Well, sine of pi is going to be 0, so this whole term is going to be gone. So r, I'm going to write over here. So r equals 1 cosine of pi is negative 1, so that's going to be minus cosine of theta. This is not identical to our original, so we X that out. It is not symmetric with respect to the line. Last one is respect to the pole. So pole, we will just use the quick one, replace r by negative r. So negative r equals 1 plus cosine of theta, and as you can see, it's definitely not exactly the same, so that is also x. So right now I'm going to highlight one symmetry, and again, sometimes there will be all 3. So one symmetry would be polar axis. Okay, so that's the only symmetry. So when we graph this out, what's happening is that the top and the bottom, if you fold on the x-axis, or if you fold it on the polar axis, the top and the bottom will be exactly the same. So let's go check it out to see if that's really true. Bam and bam, cross that out. We want to now use the technology to help us out this year. Usually we don't, but this year we are. 1 plus cosine of theta. Whoa, that is true, right? So as you can see, we do have a symmetry with respect to the polar axis. how do we sketch this out? As you know already, this is a cardioid, so go ahead and write a cardioid on it. And we want to see, normally we make a table with all of the angles, like 0, pi over 6, pi over 3, pi over 2, and so on and so on. But now we can cheat this year and use a calculator or decimals and sketch this out. So it looks like we will start at the pole. Okay, let's sketch there. Let's go back to our paper. I'm going to get a pen. Sorry, I forgot a pen. We will start at the pole, and we will go all the way to 2 units here, and it looks like a heart. So that means the top and the bottom will match up. Okay, try your best to like that. And we want to say cardioid is the shape of this graph. So we just got done with the cardioid shape. Go ahead and try this. Try these out on your calculator or on decimals and fill out the information. Once you're done, you can hit unpause and fill out the limacon without an inner loop definition. Okay, again, so this is red. Limacon without an inner loop. So we will have equations. R equals A, we can have plus B sine of theta, or A minus B sine of theta. And then we can have the other one, R equals A plus B cosine of theta or minus. Okay, so those are the equations that we can have, where A and B must be positive, and A, this is important, A must always be bigger than B to be a limacon without an inner loop. Okay, the graph of a limacon without an inner loop does not, okay, so does not pass the pole. So when you're graphing it out on your calculator or on decimals and you're starting to sketch it out on your paper, do not go through the center. So now let's go to 1F. So just like the cardioid, we will do this test for symmetry by hand, okay? Symmetry test by hand. We want to start with the very first symmetry. So that was symmetric with respect to the polar axis. And write it down of what you're about to do. Replace theta by negative theta. So R equals 3 minus 2 sine of now negative theta. As you know already, sine is an odd function, and odd, here we go. Odd functions mean a negative angle is the same thing as negative f of x. Whoa, f of x. That was tricky. Okay, so I do have a negative theta is not the same as cosine. You can't just make it disappear. You have to bring it out to the front. So if you bring it out to the front, it's like this, right? I have another negative. So now sine of a positive theta. Well, if you look at this, this is not identical to the original. So right now we know for sure it is not symmetric with respect to the polar axis. X it out. Next, we want to see if it's at all symmetric with respect to the line. Theta equals pi over 2. So the formula said replace theta with pi minus theta. Okay, then let's rock and roll. R equals 3 minus 2 times sine of pi minus theta. We will use the sum of difference of sine. So 3 minus 2 quantity. We are gonna spell it all out. Are you guys ready? Sine of pi cosine of theta minus cosine of pi and sine of theta, just like that. Well, sine of pi, that will go away because it's 0. Okay, so R equals 3 minus 2 quantity. Cosine of pi is a negative, and there's already a negative in the front, so that becomes positive cosine. Sorry, that becomes positive 1, and then times sine of theta. So here's what I got. And that means this is exactly the same as the original. So we can say that this is definitely symmetric about the line theta equals pi over 2. I will get a highlighter and I will highlight that because it's exactly the same. Now I want to do symmetric about the pole to see if that's true or not. Okay, so the pole said replace r by negative r. And immediately you can tell that it's not going to be symmetric, so we can just X that out. All right. So based on what we just studied or wrote down the definition for limacon without an inner lobe, right? Look at your A. Your A is 3, your B is 2, and A is bigger than B. So this is a limacon without an inner loop, okay? Okay, so now let's use decimals to help us out with this graph. I will now flip my computer. So I will erase the cardioid and enter in your R equals 3 minus 2 sine of theta. All right, so as you can see, it is definitely not symmetric about the x-axis, aka the polar axis, but it is symmetric about the y, aka the line theta equals pi over 2. Okay, as you can see the origin, would you agree that it does not run through the origin? But it looks almost like, right, like a lazy heart, okay? Or almost like a bean, okay? So what we want to sketch that out is the 3 pi over 2 looks like you have all the way down to negative 5. So we're going to plot that. So let's see, 0, 3. Okay, so I want to plot all of those dots. 0, 3, and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this is also 3, and I want to see what's pi over 2, what was the radius for that one? 1. Okay, so pi over 2, 1. Okay, so the shape looks like it goes out a little bit, and then it loops back all the way here, just like that. That's some ugly limacon. Oh man, I'm gonna try that again. I'm gonna flip my computer back. That's really ugly that I just, okay. Let's see if I can make it Y. Wee, down, okay. And then up, wee. Well, the right side's a little bit better than the left. I missed some dots, I make it really fat. As long as you don't touch the center and all the major axes, positive X, positive Y, positive, negative X, negative Y has all those dots, we are good.